Okay, well, I want to thank the organizers for inviting me. It's a great privilege to be here. And I'm Emeritus Professor at UCLA and the Chief Scientist on SOFIA. I have the SOFIA hat. Ask me anything about SOFIA, because proposals are due in 2 days. I know some people are actually not here because they're writing them. So, today I'm going to talk about Mauna Kea and my experience here. So, in my 15 minutes, I may take a few minutes longer. I'm going to talk about the NASA IRTF and Voyager support. Dave already talked about something we did after Voyager went by. They discovered the volcanoes, and then Dave characterized the volcanoes, and that we advertised that at the IRTF. He did fantastic work out to 30 microns, which you couldn't do anywhere else. So thank you, Dave. And then the discovery of the first L-dwarf star, and that was done on the IRTF as well. And then talk about the massive black hole in the center of the Milky Way, and some of the work I did with Chris Selgren, who was here yesterday, and Don Hall on the IRTF and the UCUR. So I'll mention that, and then go on to work on the Keck telescope. And then finish with something I wasn't involved in, although I was a collaborator of all of the people on the paper and some earlier work. So, and it was all done at Mauna Kea, so I want to mention it. I haven't seen it here. Maybe someone will show it in the future. Then a summary, and then if I have time, I'd asked Alan, I talked to Charlie Lindsay last week, and he wanted to be here. And I just want to say a little bit about Charlie, and so, if you allow me. Okay. By the way, talk about being here makes me emotional. And it is the mountain. It is that mountain. I remember driving up, and behind the CFHT, they were hauling the spurs for the telescope, or the, you know, the big whatever, up. And I got caught behind it. And I got this feeling, I am in a very special place on Earth right now. And that's the way you feel when you go to Mauna Kea. It's a special mountain. We have to remember that. Many people have talked about that, but it is true. It is just a very special place. Okay. So, in the spring of 1977, John Jeffries gave me a call and offered me a position. He wanted me to consider a position at the IRTF as the division chief, not the director. That's a whole nother story, but I'm not going to go any further. I was the division chief. So I came to the IfA in July of '77, started working with a great group, Jerry Smith, who brought the IRTF in under budget. He had earlier worked on the Mariner spacecraft with Neugebauer, and Neugebauer got him to work here on the IRTF. That was my advisor. And then a group that he gathered, oh, by the way, Jerry went on to build the Keck with Jerry Nelson. The two of them really built the Keck with Hans Bosgaard. And then Hans Bosgaard, we've heard about Hans, and we know about Hans. I mean, he is the man that made that hardware on Mauna Kea. Jim Harwood, you know, we met him yesterday. Rich Capps, you haven't seen here. I wish he were here. He came a year before me, a scientist from Arizona, and really worked with me and all the others. And there were others as well, Ed Irwin, and we hired the operators, Ron, and yeah, pretty good. I'm missing Barbara. I'm getting old, I forget first names, so. Anyway, I'm glad they're all here, our first operators. So one of our primary focuses was to get Voyager images at 5 microns, because that's why the telescope had been justified. We needed to do it, and that was, the telescope started in 1976, so it was in 3 years we were going to build this telescope, and you saw it yesterday. It was over in Italy and came over and then had to be put together and run. So many people at NASA, including the IR imager PI, Rudy Hanel, said it couldn't be done. We could maybe get the telescope working, but there was no way we were going to get images. We didn't, no cameras in those days, so you had to develop a system that would use single pixels, put it together to make an image of Jupiter. And Jim Westphal had done it at Palomar, but he knew that we couldn't do it here in Hawaii. So with the graduate student, Chaz Weichman, and you have seen Chaz, and he's here. Dana Backman, who is not here, another student. They were both students here at IfA, and many others proved them wrong. And Rich Capps was critical in this. And in 2 months before the second flyby, which occurred on 9th of July in 1977, we did get the images, and it was published. Terrell, he's the fellow that worked with Westphal at Palomar. Capps, myself, and Cruikshank. So this is the image. I just love this image. The hot spots are where you can see deep into the atmosphere of Pluto, and it's hot. So the black is hotter. And this is just the way brown dwarfs, brown dwarfs and planets, exoplanets work as well. You see deep. So this was a really nice demonstration of that. And this isn't the best image ever obtained of this phenomena, but it was done to support Voyager, and that's what counted for me. And by the way, I don't know if Tom McCord is here, but his processing people did the actual image. And we used the Chaz box, which was Chaz Weichman's thing he used for solar astronomy, I think. And he and Dana were able to put it together. You can talk to Chaz about that. I just said, go off and do it, and they did it. Okay, here are just a couple of photos. On the left is Charlie Telesco, and that's a kind of doer. Rich Capps brought him from Arizona, Kitt Peak, and and we put it at the back of the telescope just like that. And there I am on the telescope, and the amazing thing are those white shoes. Why did they have white shoes on the Mauna Kea? But as you see, I also had a beard, still had long hair, but those were cowboy days for me. Okay, so changing the subject, a few years later, and a lot of things happened that we already heard about, the imaging at 20 microns and working with Gareth and Charlie Telesco, many discoveries both of galaxies like 1068 and many H2 regions. But in 1988, Ben Zuckerman and I used the IRTF to search for faint companions around white dwarfs. And we found one new companion, 165b, and published the paper. We resolved a point source at a distance of 4.5 arc seconds, which is 120 AU at the distance. This white dwarf has a very good distance. And the temperature was 200 Kelvin. It was at that time as cold as any substellar object. There were mass loss stars and giants that were colder, but in terms of something that was a star or a substar, this was the coldest, and its luminosity was also the smallest by almost a factor of 10. It was 10 to the 4th L sun. And we did show that it was a physical companion. I'll show that in just a minute. Then, okay, hopefully that's you guys. That's my computer. Okay. All right. Davy Kirkpatrick was just getting his PhD, and Todd Henry at the University of Arizona were taking spectra of M stars, and they decided they'd take a spectrum of this thing. And it was different than anything they had ever seen before. So this then, they're very red and had spectral features at 1 micron that were not seen. So this became the first L-type object. And GD 165 was the first new classification of stars in over 80 years. Something is. I'm not sure. What's the next one? Pardon? Yeah, I don't have it on my computer now, but that's all right. So this is, let's see, let me just go back and make sure I didn't miss something. Oh yeah, and it's probably the first image brown dwarf, but we couldn't say that in the paper. We just said it's a probable brown dwarf based on the luminosity and temperature, because that was all model dependent and the age. But it was certainly the first L dwarf that had ever been discovered. So this is an image that we took. It was in the paper. This was taken by an 8x8 that Don Hall and the IMS team was developing, and Klaus Hodap and John Rayner helped produce this image. And it's at 1.2 microns, 1.6, and 2.2. And you can see the top is the white dwarf, and the bottom is the B, the L dwarf. And basically on this image, although you can still see it at 1.6, disappears, and it gets brighter at 2 microns, whereas the star, the white dwarf, gets fainter at 2 microns. You also see the proper motion, that, and that's just as a function of time from 1988, when we made the discovery, up to 1991. That's the position angle between the two, and it's basically constant. If they were, if B were a background object, it would have followed the line. So that was proof that it was actually a physical companion. So we had the coldest object, dwarf object that had ever been found, and we also had a companion. The first really definitive LT dwarf was discovered a few years later in 1995. But this was, I think, a great discovery for Mauna Kea. Not just because I was involved, but it was a good discovery. Okay, so now let me talk about the black hole in the center of the Milky Way, which I have been interested in for years, ever since I made measurements of the galactic center. Didn't think there was a black hole there, but I thought there was something, some AGN or something, but nice that it was a black hole. People had been talking about it. So in the mid-'80s, graduate student Martina McGinn, Chris Selgren, who was here yesterday, and Don Hall and I had made measurements. Previously, Chris and Don had made measurements of a broad helium line, and that indicated there was something weird going on there. And then Charlie Towns was also measuring gas. But to really make progress, you have to measure the stars. So we decided to go after the radial velocities. And we did this on UCURT and the IRTF, and we found evidence, probably the best at that time, because it came from the stars, of an excess mass of 3 to 5 times 10 to the 6 m sub sun. And we also showed that a weird phenomena that the stars peaked up, but the CO from the late type stars that we were monitoring actually went away when we got close to the black hole. And I'm not going to say anything about that unless people ask me a question. So, in the early 1990s, Don Hall, I remember this clearly, suggested to me that someone should try to measure individual stars. I don't know why I didn't have the idea, but Don is a smart guy. And Doug Simons and I we did try some of this. We also tried occultations, and I'm not going to talk about that. But we tried this on the IRTF. We never published a paper, but Doug did say he had a poster on it at one Genzel also used the ESO 3-meter telescope in the early 80s, and he had a bit more success, and I'll come back to some of that in just a second. When I went to UCLA, I went in 1990, but Mark Morris and I convinced Andrea. Yeah, she was at the University of Arizona at that time and came to UCLA, I think in 1993. 1993. And at that time, Mark Morris and I tried to convince her that with the new Keck telescope, we could actually do this measurement of the stars that Genzel had some really early work on and do a lot better job. Our first observation was in 1995. The reason why it was 1995, the first year we put the proposal in, the TAC said, yo, you guys are crazy. You'll never get this speckle. It was speckle that we were using. This will never work. So we had to wait a year. And we got the first publications 3 years later. We got, and the full spectrum and radial velocities in 2003 gave the full orbit. Let me say just a little bit about the first publication, which was in 1998. Reinhardt and his group at the VLT had published with very big error bars. They were not using the 8-meter at that time. They were using, the Keck came on before the 8-meter in the VLT. Had very large error bars. I went to Kyoto and Andrea was there, and we met with Reinhardt, and we showed him our data that we had for the 3 years, and you can see all of them, the stars that we had clear signatures of high velocities, and he really kind of gave a sigh, like, oh wow, I got it right, I'm really happy. So I give Reinhardt credit. He had the first publication, even though it was maybe a 3 or 4 sigma result, but the Keck data really proved it, and everybody at the Kyoto conference, or the IAU, felt that way. And just a few years later, we got the first accelerations. That was done at Mauna Kea, and the first spectrum was also done at Mauna Kea. So those were all first for Andrea. But the real breakthrough occurred in 2004 when we started to use the Keck telescope with adaptive optics and laser guide stars. And I want to show the next slide in honor of Don Hall and everybody else that was involved with adaptive optics and everybody that was involved with large telescopes. This is an image of the galactic center, both taken from Mauna Kea. The left one was taken by Forrest et al., Judy Pfeiffer and Bill Forrest, with one of the first arrays that existed in the mid-80s. It's at 3.7 microns. And the right, 18 years later, is from Keck with adaptive optics using a laser guide star, same wavelength, and you can see the difference. I mean, it is like opening your eyes. And it has to do with the larger arrays, it has to do with the adaptive optics, and it has to do with the large telescope. All of them put together, and they have to be integrated. But it was done. And by the way, they got the position of Sagittarius star wrong, as you can see. That little X in the middle, if you can see it, is where Sagittarius star is. And now, actually at this time, every time we would look, there'd be some hint at 3.8 microns of Sagittarius star present, and that's important, as you'll see. Just show it to 90% of you have seen it. How many have not seen this movie before? Okay, just enough that I want to show it again. This is orbits of stars over, in this case it was 15 years, and orbiting around the black hole. It's 1 arc second on a side, 0.1 you see over there, and the images that we're getting are near the diffraction limit at 2 microns of 0.05 arc seconds, or 50 milliarc seconds. It is not the actual data, but it's where the stars go. So let me show it again. Okay, you see where Sagittarius star is. Then you see the first one coming in, whips around the second one. The second one's the most important, that's SO2. The other one's SO16. Both of those are going 3% the speed of light as they whipped around the black hole. And of course, this is just following Newtonian physics, but it did do that. Now with SO2, we have the full orbit, and in 2018, it's going to whip around again. And now we're going to go for the relativistic effects, and I'm not going to go into that, but just let you know that that's what's happening this coming year. And we're still doing this on a regular basis. This shows an image, a two-colored image. The white are stars, and it's a three-color, so that things that are red are mostly at 3 microns. And you see Sagittarius star. This is sped up a factor of, so 1 second is 1 hour, and it's looped around. But you see that Sagittarius star goes up and down, and it's very red. So this is just a visualization that Sagittarius star is seen most of the time at 3.5 microns. It's there against the stars, and there are a lot of stars in the background, but you see it at 3.5. You see it also at 2.2, almost continuous. Okay, because of that variation, I proposed with Andrea that we try to do a time sequence at 2 wavelengths using 2 telescopes, so 2 imaging at one time, and then you have to use 2 lasers. So we got this beautiful picture of 2 lasers going on. There was a later time when we were doing this that actually Subaru and Keck was, Gemini was also observing. There's one image with 4 lasers pointing towards the galactic center, which of course is right there because the railroad tracks lead there. So that's obviously it. But I love this image. This was actually taken that night by somebody that happened to be up there when we were doing this measurement. And I'll just quickly show the data. This is black is 1.6 and red is 3.8. And you can see that the red actually lags by a minute or so the black, the 1.6 of the, we don't understand this yet. Maybe it's it's just the general lag you have at longer wavelengths because of the expanding electrons, but it could also be a relativistic effect. And we actually, this was done in 2012. We're still writing the paper on this one. Some things take longer to write than others. Okay, so I want to finish with this. That's the search for planets around young stars, and in particular an image of HR 8799. This is work by Christian Moreau and Bruce McIntosh, who was my student, just like Doug Simons is. So Bruce and Doug are 2 of my real prizes, and Chaz Weichman, 3 prizes. I probably have others too that I'm forgetting at this point, so I apologize to anybody, but Bruce, Doug, and Chaz are really my 2 of my prizes. And then Ben Zuckerman, who's a longtime collaborator, did the L-dwarf stuff with me. And they published this in Science in 2008. And it's high contrast adaptive optics imaging with Keck and Gemini around an A star, HR 8799. It'd be nice if it were around a G star, but that is yet to come with better adaptive optics and bigger telescopes. But they found 4 high-mass planets around this, orbiting in the same direction, just like in our solar system, at 14, 24, 38, and 68 AU from the star. And you can go to Wikipedia if you want to see the movie, but I actually have the movie in the next slide, and I'm going to show it. But it is the best evidence that I feel that exoplanets form around main sequence stars, like planets in our solar system, actually orbit in the same way. How many of you have not seen this movie? Okay, that's good. So there it is, 7 years of Keck data, and those are planets around that star orbiting, and you can see the inner one is moving the fastest. The other ones are moving slower. They're all moving in the same direction. Now there are details. They even have spectra of these now. And this is all done at Keck. And to me, this is a crowning glory of a great observatory. There's more to come, of course. All right, so observing at Mauna Kea for the past 40 years has been fantastic. And working with the IfA 13 years from 1977 to 1977 to 1990 was a great privilege and a lot of fun. And Mauna Kea is the best site in the world for visible and near eye observing. I'll say that without any hesitation. It has the best and largest telescopes and has among the best instrumentation. And in many areas of astrophysics research, it is doing the best and most important work. And thanks to the directors, faculty, staff of FA over the last 50 years that have worked so hard to make all of this happen. I realized, do I have time to talk about Charlie? Okay. And I realized I did actually go quickly over a point that I wanted to make on the Galactic Center. I actually missed a slide. But I'm not going to go over the whole slide. Just want to, I've said everything here, but I just wanted to note that the work done, the massive object comes from orbiting stars seen, and the work done at the VLT, Gensel et al., he had the first paper, and the Keck observing. Keck has higher signal and noise at 2.1 microns than the VLT. Because of the larger telescope, they're an 8 meter, we're a 10 meter. That helps a lot because the image is smaller. Better AO system, and it's a better site. It's 2 times actual measurements at air mass 1.5 versus their 1. And Gunther Witzel, who is now at UCLA and got his degree at Cologne and worked on the VLT, has many past data, and he swears that this is right, that it's about a factor of 2 better. Now part of this, I realized as I was putting this together, goes right to Doug's slide about the summer, winter, because they observe in the winter time, and they have high winds, and that causes the scene to be degraded. So some of this is a summer-winter thing. We consistently get better images, and it's just amazing to me, and everybody agrees that, however, the scene is critically important. If the scene is bad, we don't get good data on the Galactic Center for the orbits. We have to have that good scene, but it happens most of the time. All right, now let me just talk about Charlie. Okay. Charlie Lindsay, the solar eclipse observations on the Kuiper and also on Mauna Kea. I met Charlie, he was working on the 88-inch, putting up on Mauna Kea. Both started on the 88-inch and then went to the IRTF. He put black polyethylene over both of them. And I remember once at the 88-inch, he's working with Chaz Weichman, they were trying to do a solar eclipse and see if they could see the extreme, but it wasn't a full eclipse. And I said to Charlie, well, let's do a full eclipse with the Kuiper. And he actually liked the idea. So we did it. We did one in 1991 over, 81 over Japan, and then 88 over Guam. And we determined the height and temperature of the extreme solar limb. Many papers by Charlie Lindsay. He's always the first author. And we showed that Beck et al. Using the Concorde, that has somehow made a mistake, but I don't know. Here is Charlie on the right, and he wanted to be here, and he has a patch over his eye because he's flying in the airplane, and wanted to keep dark adapted so when you looked out you would see. So that's the crazy thing that Charlie did there. I'm on the left, and Mike Werner, who was kind of leading the things at NASA Ames for the Kuiper at the time. John Jeffries was involved in this. We got some beautiful data. We got the height of the limb, the observations, including a measurement at 1.2 out here at the very end, done with the 1991 solar eclipse, and the model is in the circles. So with that, I'll thank you very much.
Thanks, Eric. Questions for Eric? Chance.
There's one bit of history about the Voyager experiment that just highlights how life was back in the day. The Chas box you mentioned had to take 2 inputs. The way we made the images is you'd scan the chopping secondary up and down while tracking the telescope to follow, and you sort of just, actually would turn the telescope off so that the planet would just move and synchronize everything to get data in the small pixels that we had. So it took 2 inputs. One was the output of the lock-in amplifier. Who knows what a lock-in amplifier is? You're over 50. And a trigger from the chopping secondary. So I was back in Honolulu. They were up making the observations. Before the telescope had even been commissioned, I get this frantic phone call, something's not working. So I get in a little airplane because I was flying myself over, flew to Kona, drive straight to the summit, shoot all these guys out of the room, and went to the back, and one of the inputs into the Chas box, I think the chopping secondary, was going into the wrong B and C connector at the back of the box. So that took me about 30 seconds to figure out. But I stayed in the control room for at least half an hour, just so it looked like I was doing something. And it got connected, and then it all worked and made these fabulous pictures. But looking at the universe through a soda straw with 1 pixel arrays was a hard way to go.
Thank you, Chaz.
I just had a quick story to tell about Eric in the old days of infrared astronomy, where we had a single element bolometer, and I was Eric's operator one evening, probably looking at a brown dwarf, and the data collection computer went down, and we could not observe without that. But it was a clear night, and Eric was not going to give that up. And he sat there reading numbers off the voltmeter, and I was writing them down on a piece of paper. And I don't know if we ever reduced that data, but
we certainly did.
It certainly shows his tenacity.
Well, let's thank Eric again.